by this value, which is 3.08 into 10 power minus 3. Simplify this and calculate the value. Usually percentage error for VCQ, which is 7.77 minus 8.76 divided by 8.76. Don't forget to multiply with 100 because we have percentage. First one you get it as 10.7. One of you are able to get this 10.7, and for second one you are able to get negative because this is smaller than this. See the answer for the second one. How much the answer per second? Yeah, 11.3%. Minus 11.3%. Can you comment on these answers? Same problem. The problem remains same, but the method of obtaining operating points are going to be different. You can see using accurate method, which has given the smaller value of conductor current, which is 3.08, but larger value for conductor current in approximate method. You can compare these two values, 3.08 and 3.4. That's why you got here the positive error. Here the negative error. Okay. But what you want is error must be 0. You don't want even negative percentage here or else the positive percentage here. Error must be minimized. So in this case we can see that for ICQ we got a positive error and for ICQ we got negative error. It is deviating away from the error free. Okay. So that's why among all these both methods, this goes more positive and this goes more negative. Compare this is somewhat better. Plus 10.7 is going to be better. This is more negative. Minus, if you take absolute value of both, what will be the answer? This remains as 10.71 and this remains as plus 11.3%. This error is going to be more compared to this if you take absolute values of both errors. Okay, just a comment on this problem what we have done in the last class. So today's class we will introduce a new type of configuration, bias configuration, which is called as color-fed to base bias configuration. Before that, if you have any questions regarding the voltage divided bias, you can ask us. Take reading as a color-fed to base bias configuration. Or else this is also called by another name, which is feedback bias configuration. This is the last type of configuration that we are going to study in the common emitter configuration. Look at the syllabus where we started with common emitter configuration, and that this is going to be the fourth type of biasing circuits discussed. There is some intention why we call this feedback bias configuration, because this circuit what we are discussing in today's class also provides a negative feedback into the input. Some portion of output we are taking and provide the feedback. To provide feedback, definitely the stability will be good, but the feedback in turn decreases the gain of the circuit. So write the circuit diagram, and later on you will see that how this decreases the feedback, decreases the gain of the the circuit diagram for collector to base bias configuration. Where positive peak is going to be 5 volts, negative peak is going to be minus 5 volts, so peak to peak is going to be 10 volts. Assume that if I add a DC voltage about 5 volts, what will happen to this waveform? Anybody guess? It moves 5 volts. So whatever the zero crossing you are seeing here is actually occurring at the exact middle. That means the positive off cycle is exactly as negative off cycle. But when you add the 10 volts of DC to this waveform, you can see the waveform fluctuates like this. This is your zeroth axis, and you can see that my peak to peak still remains as 10 volts. Now see where the levels has been shifted. Okay, so now it is again the 5 volts here plus 5 volts, again 5 volts here. Just taking this. That this same wave, when I add DC to this will rise. That's why you see the output of a clapping waveform like this. Exactly it does this. Okay. Because addition of DC makes your AC waveform to shift above. And also that depends upon type of DC what you add. In this case I showed an example of addition of DC as 5 volts plus 5 volts. Suppose in case if it is negative. If DC is going to be minus 5 volts, what would happen to this waveform? It is pushed down. That means your zero axis will be something here, and your waveform will be something like this. Right? It will be pushed downwards. That depends upon the DC voltage. You see in the circuit you have a reference voltage. Right? Normally we add 2 volts or something. You try to make it to apply peak to peak sine wave as 10 volts and try to apply DC as plus 5 volts and observe the waveform. It will be of this type. Apply minus 5 volts and observe the waveform, it will this way. That means peak to peak voltage will not change, but everything is shifting will change. Okay. So why I discuss that is because if you apply these kind of waveforms to the amplifier input, here we assume that the signal does not have DC. If in case any DC is coming here, that is blocked by this capacitor. Okay. Because DC should not alter this operating point established. Due to that, we are using capacitor. And one more important feature of this is going to be this provides a negative feedback voltage shunt negative feedback. This amplifier is going to provide. We will discuss amplifier, negative feedback amplifiers later on. So, what do you mean by voltage and negative feedback? Normally, feedback amplifier contains like this. It will contain an amplifier part and it will contain an feedback part. Same block diagram we are going to discuss the part B. Okay. Just an overview I am giving here to show that we expand this concept of voltage and negative feedback. So feedback amplifier will have 2 inputs, 2 outputs, and here you can see that we will have a load resistor here and the amplifier output. We will sample this voltage in parallel, that is called the shunt, and same thing we will provide to the input. This is called as voltage and feedback amplifiers. You can see here we are taking some sample of the output voltage in parallel, and the same thing feedback will have some gain, feedback network. We have some gain. Say gain of this is going to be beta. Now see, don't confuse this with transistor gain beta. Even though both are going to be of same notations. This is nothing but gain of the feedback network. We also indicate with same beta notation. This is totally different from the transistor gain beta common concept. Whatever the voltage coming here, that is multiplied with beta, and same thing is applied to the amplifier. Now see the phase of these two things. They are going to be out of phase. They are not going to be in phase because of negative feedback. You understand the concept of feedback? Okay. So here we have an AC signal which is applied as an input. Along with your input, actual input AC, you are going to get the feedback also. Feedback always signal must go like this. Signal cannot go in reverse. Also look at direction here. Signal must come in. Signal cannot go like this output. So feedback signal multiplied with feedback network gain beta, and that is applied to the along with your input signal. These two signals are going to be out of phase because of negative feedback, and then applied again to the amplifier. Amplifier raises the strength, and that appears as the load resistance. This is nothing but R. Same concept is going to occur here. Okay, but here circuit is going to be different as well. There are shown with the help of a block diagram. Whatever the voltage, this is our output point in this circuit. Color. At this point, we will take a sample and provide that as an input through the resistor R. And whatever the voltage we are sampling here, you can see that these 2 points. But look at here, how we sample the voltage at this point and the ground. There is some voltage. This is a sampling voltage. And now we provide an input through the resistor RB. This is your feedback resistor. Okay. And you provide that as input to the base of transistor. At this point, you observe the voltage is a feedback voltage. Along with this, some input voltage is also coming. Okay, AC input voltage through capacitor, whatever is coming here, along with the feedback voltage. So current here cannot go like this. Okay. Look at direction of feedback. How it is coming from output back to the input. The same way here also current must come like this. Okay. Because of supply here, there is some current which will indicate as IC. Whatever current flowing here, let us indicate as IB, DC current. And whatever current going here to the collector, let us say this is going to be the emitter current. So this is going to be the total collector to base bias network. The only change compared to this the circuit to other circuits are there is a base resistor connected from the output to the input. And whatever the current coming here, that gets divided across 2 branches. One current goes to the in branch RB, another current goes to the collector. That's about so this circuit can be analyzed again using our normal procedure, which is AC analysis. quickly we'll go through the DC analysis of this. Okay, how to do DC analysis? Write the DC equivalent circuit, whatever it is shown here. Write the currents and voltages, show it everything. I done a mistake here. This is current whatever is flowing to the collector. Let us call it as IC, and we will not show any emitter current because we don't have resistor here. And here current is nothing but this current plus this current is nothing but the total current, right? So let us write here this current as IB plus IC. Usually we will not show the currents and voltages in the original amplifier circuits. We need to show currents and voltages in the DC equivalent circuit, which we will write here. I am drawing a DC equivalent circuit of collector to base bias configuration. This is the DC equivalent circuit of collector to base bias configuration. Let us call this figure B. This equivalent circuit can be drawn by making your AC signal sources as 0 and the capacitor should be open circuit. Same thing what we showed you, the current in the flowing through the RC is nothing but sum of IB plus IC that gets splitted, okay, into the two branches. One is collector base emitter branch, other one is collector emitter branch. So there are two branches here. You can see one branch will be which we can apply KVL is this is base emitter. Base emitter loop, and other one is going to be collector emitter loop. And you can follow as usual procedure what we did for the calculating the quiescent current and as well as collector. Apply KVL to the base emitter loop and try to see what we can do. Applying KVL to base emitter loop, you get. That means you must apply KVL to the base emitter loop of DC equivalent circuit of collector to base bias configuration. You get it here minus VCC plus. But here drop across this. I am going in this fashion. Okay, that means in my path there is a RC. So what is the drop across RC? That is IB plus IC times RC. That is a drop across RC plus IP times RB plus VBE equals C. All of you understood this equation? Just simply apply KVL to the base emitter. From this I want to obtain expression for base current. See, there is a color current here. Can we substitute this IC as beta IB? Okay, so that this expression I can easily estimate base current. Okay. Substitute IC is equal to beta IB in the above equation. Okay. What we get it is minus VCC plus and keep it IB as it is plus beta times IB plus IB times RB plus BB, which is equal to C. Now we can take out IB as a common factor and find out the expression for IB. If you take IB as a common factor, transfer this to the right hand side, VCC minus BB, that is in the numerator. IB is taken as a common factor. 1 plus beta. RC is left here, RC. So the plot is 1 plus beta times RC plus RB. All have understood this? Okay, we obtain this equation. Any questions here? See that this equation you can compare with fixed bias, not this, it's emitter bias base current expression. What is the difference between this and base current expression for emitter bias? The change is here. In place of RC we have RE there, that's all. You understood this one, right? That means if you replace this expression in place of RC as RE, this expression becomes same as base current expression of emitter bias, right? So that's the only change. So you can write one point here, replacing RC as RE. Okay. The above expression changes to IB of okay, what bias? Emitter bias. Okay. You understood this point here? That means you can convert this circuit, what I have written here, this circuit into the emitter bias just by replacing RC by RE. Whatever the emitters there we have, replace that with RE, definitely this circuit, the base current can be modified to the base current. So further we know that to obtain the present point, IC is equal to beta times IB, right here, IC which is equal to ICQ, let us say, beta times, we write the same expression, in the numerator we have VCC minus VBE divided by 1 plus beta times RC plus RB. So this is the final expression for present calculation. Also see that, like we did in the case of voltage divided bias, can we approximate this collector current expression and make this expression as independent of beta, like what we did in case of voltage divided bias? This equation can be approximated. How do we do approximation here? You can see that here 1 plus beta times RC is there. Okay. So this can be approximated as beta. And also look at RB value is going to be much more smaller here. So ignore this. Okay, what will happen? Else you can do it another way. Let us do it here. Substitute is needed now. Look at the last IC equation there. So what we can do is, if I convert 1 plus beta as approximately equal to beta, that is the case. So look at IC expression now. IC will change to beta as it is. In the numerator we have VCC minus VBE. If if I translate this into beta, denominator becomes beta times RC plus RB. Look at now again here. Beta RC and RB is there. Which one is down? This is beta RC. Beta is, as we said last class, beta is typical value is going to be 100, 200, 300 given as 100 times the RC. This will be larger, right? So compared with this is larger. So that we can write it below here. So if beta RC is very large than the RB, okay, RB can be neglected. Okay. Since beta is going to be very large and the product of this will be much more larger, right? That can be neglected. RB will be neglected if that is the case. And here numerator also, since BB is small compared to VCC, okay, you can also neglect BB. What will be the final answer for IC? Okay, this if you make it equal to beta VCC divided by what is the total denominator? Let us rewrite it. Beta times RC is left here. This beta cancel with this beta, and IC is equal to VCC over RC. Understand this point here? That means the collector current expression is independent of all parameters except the RC. That means in this circuit, whatever we are seeing here, much more better stability can be established by increasing the value of RC. If you raise the value of RC, this circuit can offer a better stability. That's a conclusion from that. And moreover, this circuit is again independent of transistor gain beta, as well as temperature factor, and this provides stability. Next, we can go for the computation of current and voltage from the DC equivalent circuit by applying KVL to the collector emitter. Applying KVL to the collector emitter node. Just apply the expression here. What will be the expression? If you apply KVL to the collector emitter node, minus VCC plus IB plus IC times RC plus VCE. Anyway, we don't have RE is equal to. And again, here you can see that in this equation also we can do some approximations. IB is going to be smaller compared with IC, right? We can neglect this value IB so that this equation gets simplified. So you can see here IB is small compared to IC, hence it can be neglected. Hence IB is neglected. What will be the rest of the equation? Minus VCC plus IC times RC plus VCE, which is equal to C. I just want the expression for VCE. So VCE, which is equal to VCC minus IC times RC. This is also, we can make equation this to the VCQ also. This is the final expression for present collector voltage. Here you can introduce an index as this. Any questions here? Okay. So let's understand this how to obtain expression for IC and expression for VCQ. These are the operating points. That's what we obtain from these analysis. We will not do this load line analysis for this circuit. Reason is this load line analysis of this circuit is same as emitter bias calculation. If that we will not do any load line analysis for this circuit. I hope only for fixed bias configuration we did fixed bias and emitter bias configuration. We did load line analysis. Apart from that, for rest of the circuits, we cannot do the load line analysis. So there is a modification for the circuit as we said here. Now can we rewrite the original amplifier circuit by adding an emitter resistor and see that what will be the expression for IC and DC just by using some intelligence concept without deriving all these things. Okay. Can we obtain the expression for ICQ and DCQ? Look at this. Do you understand my point? What is modification here is? I've just added the resistor here RE. Now I am asking you, can we obtain the expression for ICQ by triangle inspection? Let us write. Don't spend time by applying KVL and all those things. Looking at this, inspection of this, and looking expression of ICQ, can change these expressions. Where this addition of this can be included in the expressions. Try at least before we writing the answer. Some of you can try that. Try at least some of you. First write the expression for base current. Later on write the expression for IC. And finally write the expression for DC. Anybody has written on this side? IB expression. Modified collector to base bias. It is called as modified collector. That is equivalent is already here. Expression for IB is going to be here. IB is as usual in the numerator there will be VCC minus VBE divided by 1 plus beta times. Here we have RC plus RE plus RB. We got this expression. That is the expression for IB. Once you know IB, it's very easy to obtain the expression for IC. IC which is beta times VCC minus VB divided by 1 plus beta times RC plus RE plus RB. VCE which is equal to VCC minus IC times RC plus R. So these are the expression for this. home we can try it by applying KVL to the base emitter loop and collector emitter loop. Get the same answer. There is one small drawback in this circuit, what we observed here. This was completed. Any questions here? Okay, any doubts in this circuit? All have understood how to obtain these equations? Go back on home and try with applying KVL to these two loops. We'll end up in these expressions, right? Okay, now look back at the circuit. Why I have taken this circuit is because addition of RE improves stability much more better. But the problem with this is again because of it's two feedbacks associated here. One is this emitter resistance introduce a feedback, also this collector to base there's a feedback. Both are negative, so gain of this circuit decreases. But for the original circuit, there is some technique to modify in such a way that the feedback, whatever it is, decrease because of the gain, whatever decreases because of the feedback, that can be overcome to a certain extent by splitting this resistor into the two halves. What I will do here is I will use two resistors here, and whose value is going to be RB by 2, RB by 2, and the junction of this I will use the capacitor here. This is a modified version of this circuit. Look at this. What will happen if you go for the DC analysis for this circuit? Look at that. What will happen to the DC equivalent when you want to write the DC equivalent of this? Okay. See, for DC equivalent again there will be the selector here. You can see that this capacitor will be removed. RB by 2, RB by 2 will become again RB is that is the same as the original circuit. No problem with it. What about for the AC? AC conditions. Because you will consider two conditions also. Right? When you consider AC, this capacitor will be there, and look at where your signal will flow. That's important for us. It will go through the RB by 2 resistance, because there is a jump here. You can see that whatever capacitor passes the AC signal, it will go through this, and this also RB by 2 will be introduced as a feedback to this. Right? That means there is some the resistance introduction. When the signal goes to the collector terminal here, it's act like almost like bypass capacitor. For AC signal, this will be like a short circuit. Whatever signal coming here at the capacitor suddenly goes to the ground here. No problem. But it will experience some amount of resistance here. That's the problem. But for DC analysis, same circuit will be RB whatever value the original circuit that has been retained here. There is no changes with respect to DC analysis is concerned. But look at the feedback. What feedback we are going to experience here? Is it same as the original circuit? Look at the feedback. But feedback is same as this because whatever for DC circuits, this will not come into the picture. Feedback is the same as that. But only for AC signal, this additional resistance will be included. Because instead of signal, because you can look at here for AC signal, this will act like a short circuit. Current instead of going through this, suppose if some portion of current goes through this, RB by 2 will be the additional resistance. It's a bottleneck for us. So this is just a modified version of this, and you did not go depth analysis of this circuit. Just it's an extension of breaking the RB into the two halves so that the original DC conditions will not get altered. So for this circuit, if anybody asks you present the current expression and present current voltage, it remains same as the original collector to base bias configuration expressions. No changes. Any questions here so far? The time? We have 2-3 minutes to take one problem quickly. Take down this problem. Determine the operating point. Otherwise, whatever we have done so far, it is going to become waste, right? Don't solve the problem here. Determine the operating point of the collector to base bias circuit. Determine the operating point of the collector to base bias circuit. For the figure shown below, full stop. The value of transistor gain beta is the value of transistor gain beta is 100. The value of transistor gain beta is 100. And the base emitter voltage VBE of the transistor is 0.7 volts. Full stop. Also find the percentage change in the value of operating point, when the value of beta increases by 50%. When the value of beta increases by 50%, 50. Take down this circuit. Here is given circuit. RE which is given as 1 kilo ohm, RB is 200 kilo ohm, RC is 5 kilo ohm, VCC is 15 volts. The DC equivalent circuit is already shown. Direct same equivalent circuit. Straightforward problem here. Just apply KVL to the base emitter loop and try to obtain expression for ICQ and VCQ. First obtain the value of IB. Later on you can go for the calculation of IC. For total of Srinidhi.
Present, sir.
Subhadas.
Yes, sir.
Subham Krishna.
Yes, sir.
Sudanova.
Present, sir.
Suresh Singh.
Yes, sir.
Tanay Agarwal. Tejas.
Present, sir.
Tejaswini. Dakyu.
Present, sir.
Rushita. Vignesh.
Present, sir.
Vishwas. Vaibhav.
Yes, sir.
Vidya. Vishnupriya. Vishnushri. Vishnushri. Vivek Kumar. Vivek.
Yes, sir.
Diyani. Yoshita. Yukti. Rashida. Rachit. Abhilash. Abhimanyu.
Yes, sir.
How many classes did you present? Are you present all classes?